So recall that with level curves, we took a function such as f of x y equal to y minus x squared, which can be visualized as a three-dimensional surface. And we considered representing that three-dimensional surface in 2 dimensions by these level curves or contour maps. For part A of this extra problem, let's draw the contour map or level curves of f of x, y for values of k equal to 0, 1, 2, and 3. So we were looking at the curves when the function f of x, y was equal to k. So for k equal to 0, we're looking at our function y minus x squared equal to the k of 0 in this case. So this would be a parabola x squared plus 0. So on the xy plane, this graph would be a simple parabola touching the origin 0, 0. And this is the level curve for k equal to 0. When k is equal to 1, we would have something similar. Y minus x squared is equal to 1. So y is equal to 1 plus x squared. This is a parabola shifted up 1 unit. If we take this and graph it on our xy plane, this will look like this. So again, that's a level curve for k equal to 1. If you continue the scenario for k equal to 2, k equal to 3, you're going to get parabolas just the same. For k equal to 2, you'll get this guy right here, and for k equal to 3, you'll get that guy right there. So these level curves combined are what make up the contour map. And this contour map gives us a 2-dimensional representation of the surface that is in 3 dimensions. If we were at this point x comma y, let's call it a comma b. If we decided to go towards the right-hand side, judging from these 2 level curves, the level curve on the left-hand side has a height of 2. The level curve on the right-hand side has a height of 1. Going from the left to the right, I would use these level curves to deduce that I would be going downwards on that 3-dimensional graph. If I were to be going in this direction, upwards, judging from these level curves, the guy on the bottom is a level curve of 1. The guy on the top has a level curve of 2 for k equal to 1 and k equal to 2. So I would be going from an elevation of 1 to an elevation of 2. So judging from these 2 level curves, I can deduce that if I traveled upwards, I would be going up on the graph in 3 dimensions. In section 9.2, we talked about partial derivatives with respect to x and with respect to y. Again, if we're going to the right-hand side, that's making our x increase. So you would be considering the partial derivative of f with respect to x. And since we said we would be going downwards, this would give me an insight that the partial derivative would be negative. And if you're going upwards, that means you're increasing your y values. letting us know that we're working with a partial derivative of f with respect to y. And we said that if we're going upwards, we would be going up in our three-dimensional graph. So that would give me some insight that the partial derivative would be positive. Okay, so we can get a little bit more insight of these level curves by graphing things out in our GeoGebra 3D calculator. So here's a graph of z equals y minus x squared. And if we're considering these level curves, then we would be asking ourselves, when does this graph intersect z equal to 0, z equal to 1, z equal to 2, and z equal to 3? Z equal to 0 is just the xy plane, so it's just the flat surface there, and they would intersect at this parabola right here. If z is equal to 1, give me 1 second, please. Let's see if that fixes it. If z is equal to 1, then this plane in green would be elevated by 1 unit, and it would cut through this blue surface about that parabola. If z is equal to 2, this plane will go 1 unit higher, and it will cut through this surface in that parabola. So the parabolas that we're using are the level curves that we computed earlier.